Okay, stop, or sorry, welcome back. This is part two of the lecture for working with shapefiles. Um, so uh, here I have our buffered outline, all right? And the study area geology and the buffered shapefile are always gonna have this this geometry, WGS 84 pseudo Mercator. That's just the original one, and if we say it's different, then it just reprojects. But what we're going to want to do is make sure we save it to the reference or to the CRS that we want to work with. Okay, so we've got this buffered shapefile, and what we're going to want to do now is export it as a shapefile and save it. So if you right-click on it and you say export, save feature as. There's a whole bunch of ways you can save it. We're going to save it as an Esri shapefile. Name you get to choose. All right. I'm going to call this one alluvial outline 2. Second time I've done this. I'll hit save. All right. Actually, I'm going to call it 3 because I've done this will be the third time. All right. Now here's where I get to set the CRS for what I save it as. You want to save it. It doesn't actually matter exactly what you save it. You just want to know what you save it as. But I'm going to save it as NAD 83 2011 UTM Zone 12 North, and that's this EPSG 102059. All right. Everything else should be automatic. So you hit OK. It's going to add the saved file. So here's alluvium outline 3 now. I can double click on it. I can see that its CRS is NAD 83 UTM Zone 12 North. Good news. Okay. All right. So now, now we can use this to set a mask, all right, for our areas. And what I've done is I'm going to provide you guys with a example notebook that that reads in. So here's the notebook here. This is going to read in and the shapefile. It's going to make a grid. All right, and a grid is a different thing than the discretization package. So it's important to realize that. But it's this grid is gonna have geo-referenced information on it so that it can then intersect the grid with the outline. All right, so here's just a quick rundown of what happened. So in this first cell, we just import a bunch of stuff. Key note, there's some stuff you guys are gonna have, other packages you're gonna have to get on your computers. First is Shapely. It's a Python library for working with shapefiles. So make sure you have Shapely, all right? You also need Pandas. Should be on most of your files, but you make sure you have that. And then PyShape is PYSHP. So these other packages you need are Shapely, Descartes, and PyShape. I've included those, and you can install those Python packages quite easily. For me, I use Mac ports, and I just install them via Mac ports, but your Conda forges and Conda will be able to get these too. All right, so make sure those are installed. Okay, you import a bunch of stuff. Here, an important thing that I found is that you need to have the latest version of flopy. The version needs to be 3.3.2. If you don't have it, upgrade your flopy version. All right. So upgrade your flopy version so that it reads after you run these print statements 3.3.2. Okay, so basically what this is going to do, the first thing it's going to do is it's going to load the shapefile. So that new one we created, alluvium outline 3.shape, all right, is the first one. So I'm gonna do this. I'm gonna go kernel, restart, and clear output. All right, and this should kill everything. So the first thing I'm gonna do is run this guy. All right, and again, it's gonna print out this stuff. Here, it's gonna make a data path if we don't have it. Don't worry about that. All right, so now I'm gonna import this shapefile. All right, and I'm gonna plot it. And here you see a plot of our shapefile. All right, and it looks like what we had on QGIS. Good news. All right, the next thing I'm gonna do is I'm gonna create a grid, and I want my grid to be bigger than this shapefile. So I'm gonna use a method that looks at the bounds of this shapefile. All right, and here we see the bounds of the shapefile. This is the lower left, this is the upper right corner. So X, Y, and it tells me the X length and the Y length. So I know some critical information for creating a spatial grid, right? The next thing I'm gonna do is create this spatial grid. In my test model, I'm gonna make it be 50 rows and 100 columns. All right, its length is little over 22 kilometers and a little over 9 kilometers. So these are really big cells to start off with, and you guys are going to want to make this more. You want more rows and more columns, but for now, for testing, 50 and 100. The XLL, the lower left location. All right, I want this to be smaller than this number. That means it's farther over here. And I want it to be smaller than this number. That means it's farther down here. So I'm going to start my grid somewhere down here, make sure I include all of our shapefile, and I'm going to make the length longer. So this length was a little over 22 kilometers. I'm going to make it 23 kilometers in X. I'm going to add another kilometer. And it's a little over 9 kilometers in Y. I'm going to add another kilometer, make it 10. So my grid is going to be bigger than my shapefile. All right, then I figure out a bunch of stuff. This spatial reference. So most importantly, I set my model EPSG. That's the positioning code, all right? And for UTM zone 12 north, it's 26912. All right, and then I'm gonna call this spatial reference. And basically this is gonna make a grid. For now, I'm just gonna have one layer, all right? As you guys go on, you're gonna wanna make this a better grid with different layers, however you wanna do it, you know, and that's basically the main gridding component, but making the grid cells active is what we're doing here. And so for here, it actually doesn't matter that we have a Z dimension. I'm just putting a place marker here. Okay, now we're gonna make a grid, and this is a structured grid, and it's gonna have this spatial reference information. So this is the actual structured grid for mudflow using flopy. So this call here is going to make a structured grid and plot it, and it's going to be referenced to this spatial reference using the lower left and the corners that we used. It's going to be the same length, all right, and it's going to be one layer. So pop, here's what our grid looks like. And what the main thing I want you to do is, okay, x-axis 24,7,500, you know, 24,500. So you can tell we're in the same unit, all right? Okay, so now we want to basically overlay our shape onto this grid file and find the areas where it intersects. So here we're going to use this functionality from flopy. It's called a grid intersect. And it uses our grid, and then it's going to intersect it with our shape that we made the alluvium. And especially as your grid gets bigger, this is going to take a little while to run. It's got to search through all of these. It's got to compare it to the shapefile, and so it takes a little while. And in all of these, there's a lot of detail, like what it's grid intersect doing, and the best thing to do is just, the way I figured this out was just to go to the flopy website and I actually just start reading the documentation. Okay, so boom, I'm gonna run this. It's gonna take a little while. All right, but now it's done. And result is basically this intersection, and so we can first of all look at a data frame of what result is. And there's a few things. It's pandas, don't worry about it, but this is what's called a NumPy record array, and it contains a whole bunch of different records. And the first one is the cell IDs, and these are the row and column IDs of all the cells that intersect our grid. All right, and then these are the vertices. These tell me the actual locations in space of the edges of the cell that intersect. It has the areas. All right, so this could be important when we're looking at things where we want to know, say, conductance, and we're interested in the area across which flow can occur. All right, so what we're going to use is these cell IDs. So first of all, let's just create a plot, and this is going to create a plot with the grid and then with the polygon, and it's going to highlight with the alluvium, and then it's going to highlight the cells that are intersecting it. Okay, so here's our spatially referenced grid. Our buffered alluvium outline is on top of it, and the cells that intersect it are highlighted. All right, so now remember that if I can have this big grid and there's tons and tons of cells in here, and I don't want to use them all. In fact, the only aquifer that I'm interested in is this alluvium one. I can use iBound to decide which of these cells I'm going to simulate on, right? And now I've got a really good way to set iBound. I just go through these. I'm going to make an iBound that's the same size as my grid, all right? I'm going to set it default to 0, and that means no flow, all right? And then I'm only going to set the ones that intersect it to be active. So that's what goes on here. I create an iBound, zeros, same size as my grid. And then I'm just going to loop through my cell IDs, all right? These guys that tell me where and when it intersects. And if for every cell ID, I'm going to set iBound equal to 1. That means it's an active cell, and it's going to try and figure out the variable head in all of them. So I'm going to hit run, pop. All right, and now I'm just going to plot. Here I've just plotted iBound, just so it's easy for us to see. And basically iBound's got two values, 0 or 1, all right? 0 is blue and 1 is yellow. And you can see that the cells that are active are those that overlap with our alluvium. All right, so now I've got a way to constrict my simulation only to this one shapefile. All right, now, top gear, top tip, a drain, say a river package, might be the way I want to set the boundary condition of Lolo Creek and the boundary condition here along um, the edge of the alluvium. Well, I can do the same process, create a shapefile, intersect it with my grid, and now I can write the river package and the, or for example, well packages. I could export shape files of the well locations, intersect it with my grid, and I can have all of my mudflow grid data referenced to the real world and to real world coordinates. So good luck and have fun. And we'll see you in class.